In this lesson, I'm going to lay the foundation for the rest of the lessons that we'll cover in this chapter. We'll look at overview of sets. Probability, for example, uses a lot of set theory. So let's look at some of the definitions that I have here. 5.1 states a set is a collection of objects or elements. Now the objects could be numbers, they could be variables or letters or a combination. You could even have a set consisting of a set. So normally we would write a set in braces and then write out the components. So I could have the set, say, consisting of the numbers 1 and 2. So I could say, for example, 1 is an element of this set. Or say 3 is not, I put it a mark like this, is not an element of that set. So that's one way to illustrate sets. Writing the braces and then the components of the set. It could be a general statement using set builder notation. Next set, or next definition, the universal set denoted by U is a set consisting of all elements in a given discussion of sets. So if the problem you're dealing with deals with integers, for example, your universal set could consist of all integers. Or if it's dealing with people in a city, for example, it could be the population of that city could be your universal set, and so forth. Definition 5.3 states a set is a subset. A set A is a subset of set B if every element of A is also in B. And we write the notation A is a subset of B. Okay, so that's pretty much straightforward. If all the numbers you have or all the components you have in set A are also in B, then A is a subset of B. Notice every set is a subset of itself because every set contains its own elements. So I could say A is a subset of A, B is a subset of B, and so on. Now possible that a set does not contain any elements. So in definition 5.4 we have the empty set denoted by this symbol here, say the phi symbol, or a set of parentheses with nothing in it, has no elements. The empty set is a subset of any set. Okay? Because since it doesn't have any elements, all the components of the set are in any set you choose. So the empty set is always considered a subset of any set. Okay. Now sometimes we want to denote the number of elements that are contained in a set. So in definition 5.5 we have the number of elements contained in set A is denoted by N of A. Okay, so N of A represents the number of elements in A. So I want to point out here that you don't repeat elements. So if I list a set and I put, say, 1, 1, 2. If I repeat an element, you only got it once. Okay, so this set consists of 2 elements. Okay, so you don't repeat elements. If elements are repeated, then they count just as 1. Okay, so this set has 2 elements. So the cardinality, which is what this is called here, N of A actually represents the cardinality of a set, which represents the number of components or elements that the set has. The only time you really repeat the elements is if you're solving an equation. For example, you have say x squared minus 1 quantity squared is equal to 0. This is a quadratic, and the solution to this equation is 1. And remember, it's second degree, so you expect 2 solutions. So actually, it's a repeated solution. So if the only exception to repeating the elements is maybe you're dealing with a solution and you want to indicate that a particular solution is repeated, you might write this as the solution set as 1 and 1. But other than that, we don't repeat the elements in a set. Okay, now we have some operations with sets coming up here. So union of sets, A union B. This is the set builder notation that I mentioned a while ago. This is the set of all x such that x belongs to A or x belongs to B. This is the union of sets. So when you're taking the union, basically you're taking all the components in one set together with all the components in the other set without repeating. So if the first set consists 1 and 2, you put them down in the union. The next set 3 and 4, you put them down. Now had the 3 been also in the first set, you only put it down once. So the union is 1, 2, 3, 4. The intersection is the next definition. A intersect B is a set of all x such that x belongs to A and x belongs to B. So it has to be in both sets. So in this case, the example, the set consisting of 1, 2 intersect with a set consisting of 2, 3, 4 rather. The common element is 2. So you write out the set consisting of 2 is the intersection. And the next one, this is read, sometimes they use the bar on top of the A, sometimes you use a little prime here, but this is read A complement, the complement of set A. So the complement of set A is the set of all x such that x belongs to the universal set and x does not belong to A. Now in dealing with sets, especially if you're dealing with survey problems, which we'll do some in the next section, you can and I'm trying to draw a rectangle here, so let's say this is a rectangle and then this is A. Okay, so the rectangle would represent the universal set. Okay, so assume that's a rectangle even though it doesn't look like one. So that's U, and then inside I would put the sets. So I have set A. So the complement of A is all elements in the universal set that are not in A. That's what this definition is saying. So basically, to illustrate this, we would simply shade everything outside of A. So the whole rectangle would be shaded except the circle A. That's the complement. So as an example, we have the universal set consisting of 1, 2, 3, 4, 5, and A is equal to 1, 2, the set consisting of 1, 2. So you take everything in U except those components, so you get the complement of A as 3, 4, and 5. Okay. In number 4, statement number 4, this is saying the cardinality. Remember, N of A union B represents the components, the total components in the union of this. Okay, so if you're looking at a Venn diagram with, say, 2 circles, okay, then you got the rectangle over here, which looks more like a circle, but anyway, the cardinality, you would count everything in this region here, you would count everything in this region here, and everything here. Okay, you get everything there. If you just count everything, let's say this is A, and let's say this is B. If you count all the components of A and all the components of B, then you might have counted this area right here, or the intersect, twice. That's why you get this definition. If you want the cardinality of A union B, then you count the elements in A, count the elements in B, and then subtract the elements that are common to both sets. That'll take care of you counting this little portion right here twice. Now, if it turns out that the circles do not intersect, that is, A and B do not have any elements in common, then this part right here is going to have B0. and you're just going to have n of A plus n of B. Okay, but you have to be careful with that. Now sometimes you're asked to count the number of subsets of a set. Well, there's a statement here that states if a set has n elements, then it has 2 to the n subsets. So let's see why that works by looking at some examples. Give the subsets of each set. Okay, so this is the empty set. This is the empty set. And we said that the empty set is a subset of every set, and every set is a subset of itself. So since this has 0 elements, according to the statement above, it should have 2 to the 0 subsets. 2 to 0 is 1. And that's what we have. Okay. The next one has 1 element. So according to the statement, it have 2 to the 1 subsets, which is 2. So the subsets are, obviously the empty set is a subset of any set, and the set itself is always a subset of itself. So you have 2 subsets. Okay, the next one has components 1, 2, so it has 2 elements. So it should have 2 to the second subsets. 2 to the second is 4. Well, then you just list them. Obviously the empty set would be 1, the set itself, and then the component 1. This set is a subset of this because 1 is contained in that set. This set consisting of 2 is a subset because 2 is contained in that set. So you have 4. So this is handy in case they ask you how many subsets a particular set has, because in that case you don't have to find them, you just can compute it out this way. For example, this one it has 3 components, so it should have 2 to the third subsets. So 2 to the third is 8. Okay, and then you have the different subsets, the set itself, the empty set, and then all the different combinations which make up the subsets. You can see them there. There's 8 of them. The next one has 4 components. So this one should have 2 to the 4 subsets, and 2 to the 4 is 16. So this would be handy if you just wanted to know the number. It's 16. Now if they want the actual list of subsets, then it's a little bit more tedious, but there they are. You have the empty set, the set itself, and then the set consisting of 1, 2, 3, 4, and then you have all the different combinations that you can have of the 1, 2, 3, 4, taking 2 at a time, taking 3 at a time, taking all 4 at a time. 16. Okay. This concludes this video, and again, this is just an overview of sets which we'll be using in this would be actually the last chapter that we cover in our course, College Algebra. So keep tuned for some other lessons dealing with Venn diagrams, dealing with combinations and permutations, dealing with probability, which again we'll be using sets and some of those topics. So please stay tuned, and if this helps, please subscribe. Have any questions or suggestions, please post them, and we'll see you in the next video.